Hello guys, welcome back to my channel Gamma Digamma. So in this video I said let's probably get more insight on duplications formulas, and well, we already derived the duplication formula for the gamma function, so let's do it for the digamma function and apply it in places. Let's get started. Okay, so the derivation for the duplication formula of the digamma function isn't a hard job, because when we talk about duplication function, first we did the normal gamma function. So gamma of 2z was nothing but 2 to the 2z minus 1 multiplied with the gamma of z times the gamma of z plus 1 half divided by square root of pi. And since the digamma function is just the derivative of the natural log of the gamma function, which means we need to take the natural log on both sides for this guy. So we have natural log of gamma of 2z is equal to natural log of 2 to the 2z minus 1 times gamma of z times gamma of z plus 1 half, and then using properties of logs minus natural log of square root of pi. The thing is, we can again break the product down using properties of the natural log, so we can bring the power down also. 2z minus 1 natural log of 2 plus then we can break the product into addition, natural log of gamma of z plus natural log of gamma of z plus 1 half minus, then we can bring the square root to make a half, natural log of pi. Now differentiate both sides with respect to z, the argument variable. So then we'll have the digamma of 2z times 2 by the chain rule is equal to, well, we'll just have over here 2 times natural log of 2, because the derivative of z is 1 and the other guy is a constant, plus digamma of z plus digamma of z plus 1 half, and then natural log of pi is a constant, so that will become 0. Okay, fair enough. So this is the duplication formula for the digamma function. And now we're going to find some special values of things. We'll specifically use gamma of z plus 1 half. I'll make that the subject of the equation. We have 2 times digamma of 2z minus digamma of z minus 2 times natural log of 2. We're going to use this equation to find some particular values. Okay, so see you on a fresh page. Okay, so we know this formula, we just derived that, and now we are choosing z to be 1. So we have 1 plus 1 half, which is a digamma of 3 halves, is nothing but 2 times digamma of 2 minus digamma of 1 minus 2 times natural log of 2. We know digamma of 1 is negative Euler-Mascheroni constant, but what is digamma of 2? Well, to find digamma of 2, we'll have to refer back to this infinite sum representation of the digamma function. So digamma of z plus 1 was actually minus Euler-Mascheroni constant plus sum from k equals 1 to infinity of 1 over k minus 1 over k plus z. So if you take z as 1 over here, if digamma of 2 is nothing but negative Euler-Mascheroni plus sum from k equals 1 to infinity of 1 over k minus 1 over k plus 1. And then if you can write some terms of this infinite series over here, so 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3, going till basically negative 1 over k plus 1. Since it's an infinite sum, take the limit as k goes to infinity. So notice this cancels with this will cancel out with this term. We have 1, and then in the limit that k goes to infinity, this will go to 0. So we'll just have 1 for this guy, which means the digamma of 2 is just nothing but 1 minus the Euler-Mascheroni constant. So we can plug that back. Gamma of 3 by 2 is nothing but 2 times this guy, 1 minus Euler-Mascheroni, minus of negative Euler-Mascheroni is positive Euler-Mascheroni, minus 2 times natural log of 2. So we have 2 minus 2 Euler-Mascheroni plus Euler-Mascheroni minus 2 times natural log of 2, which is just 2 minus Euler-Mascheroni minus 2 times natural log of 2. That's nothing but the digamma of 3 halves. Right? Isn't that a nice result? And now it's time to take z equals 2 out for a toss. So if digamma of 5 halves is 2 times digamma of 4 minus digamma of 2 minus 2 times natural log of 2. We know digamma of 2, we just calculated that previously to be 1 minus Euler-Mascheroni constant. We need digamma of 4. So again, use the infinite series representation. Digamma of z plus 1 is nothing but negative Euler-Mascheroni plus sum from k equals 1 to infinity of 1 over k minus 1 over k plus z. Take z equals 3 now. Digamma of 4 is negative Euler-Mascheroni plus sum from k equals 1 to infinity of 1 over k minus 1 over k plus 3. Okay, so now this sum is actually going to be a little weird, but what we can do is we can split this up into, say, pairs. Sum from k equals 1 to infinity 1 over k minus 1 over k plus 3. What we can do is we can have this sum, we can have 1 over k, then from 1 over k you subtract k plus 2, or say k plus 1, and then you add the same 1 over k plus 1, but you subtract 1 over k plus 2, and then you add the same 1 over k plus 2, and then you subtract this last term 1 over k plus 3. So it's like an induced telescoping product, because a telescoping sum, because now this guy will just become the first term when k equals 1, the left hand side term, because this is telescoping. This will become 1. This you can, if you want to write out some terms, you'll have half minus 1/3 plus 1/3 minus 1/4 plus 1/4, basically till infinity, and the last term will go to 0 in the limit. We'll just have all these other terms will telescope. We'll just have half. Similarly over here, you'll have 1 over k plus 2 when k is 1 as the remaining, which is 1 over 3. So we have 1 over 1 plus 1 over 2 plus 1 over 3 for basically this sum over here. And I don't know if you can take the LCM. LCM is 6, I believe. So we'll have 6 plus 3 plus 2 over 6. So we have 9 plus 2, 11 over 6 for that sum. So we can plug that in here. Negative Euler-Mascheroni plus 11 over 6, I believe. And then we can basically finally plug this in over here. Digamma of 5 halves is 2 times this, so negative 2 times Euler-Mascheroni plus 11 over 3 minus 1 plus Euler-Mascheroni minus 2 times natural log of 2. We'll have negative Euler-Mascheroni 8 over 3 minus 2 times natural log of 2 as the value for digamma of 5 halves. Isn't that something nice? We're actually getting nice values. Okay, so since every digamma formula had this infinite sum in it, why don't we actually try to generalize this guy? So remember the induced telescoping series that I basically had for the digamma of 5 halves. I'm going to try to basically generalize for some z, k plus z in the denominator. So I'll have sum 1 over k, and all these sums are going from k equals 1 to infinity. I won't write that again and again. Minus 1 over k plus 1. Okay. Then you add the same 1 over k plus 1 because it wasn't there originally. Minus 1 over k plus 2. Then you add the 1 over k plus 2 minus 1 over k plus 3. And then you'll add the 1 over k plus 3 minus 1 over k plus 4, say, summed. And this process of adding, subtracting will go on until you have 1 over k plus z minus 1 minus the 1 over k plus z, and we don't need to add that back because you always had that. So now this is telescoping, and this will go to 1 over k when k is evaluated at 1, which will just be 1 over 1. This will be 1 over 2. This will be 1 over 3. This will be 1 over 4. So you're basically taking k equals 1 for the first term in this pair. So take k equals 1 here. You'll have 1 over z for this pair. So you're basically having 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 dot 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 1 over z for this crazy infinite sum over here. And what was this? According to some of my recent videos, this is just the zth harmonic number. Isn't that crazy? I mean, we're tying like way different ideas together, because digamma of z plus 1 is actually equal to minus Euler-Mascheroni constant plus the zth harmonic number, because now we can always generate for any z, we can always generate the formula for digamma, because if we just write these reciprocal terms, these harmonic terms for some finite z, we can generate any value of the digamma function just knowing or just summing the partial sums of the harmonic series, or that's basically the calculating the harmonic number at a particular z. And if you still don't believe me that this sum is actually equal to the zth harmonic number, well, take the integral from 0 to 1 minus x to the z over 1 minus x dx. What you do is, notice the denominator 1 minus x is of the form a over 1 minus r. Absolute value of r is less than 1, and that this thing is satisfied because x is between 0 and 1. It is in the radius of convergence, so we can use the infinite GP formula. A is 1 in our case, so we can have sum from k equals 1 to infinity of x to the k minus 1, because the first term was 1, multiplied with 1 minus x to the z dx. Interchange the sum and integral assuming uniform and absolute convergence, because we can assume z is finite, otherwise it will just diverge. Over here we have x to the k minus 1 minus x to the k minus 1 times x to the z dx. We have sum from k equals 1 to infinity, integral from 0 to 1, x to the k minus 1, x to the k plus z minus 1 with a negative in between them dx. Now use the power rule for integration. We have x to the k over k minus x to the k plus z over k plus z, evaluated from 0 to 1 though. This just turns out to be sum from k equals 1 to infinity of 1 over k minus 1 over k plus z, basically the sum that we started with over here. But the thing is, this integral, if you refer to my video on harmonic numbers, the very first video on harmonic numbers, this is just the integral representation of the zth harmonic number. The power of x in the numerator is basically the harmonic number. So that's another proof, if you don't want this induced telescoping series, another proof that this identity over here is holding true. And you can also find digamma of z as negative Euler-Mascheroni plus the z minus 1th harmonic number. Just some re-indexing there. So that's one fabulous result, because that allows us to find the value of, say, digamma of 7 halves or something. Yeah, digamma of 7 halves. We can totally use the formula 2 times digamma of, I believe, have a 6 here, minus digamma of 3 minus 2 times natural log of 2, and digamma of 6, digamma of 3 can just be calculated because of this formula basically. So digamma of 6 will just be 2 times minus Euler-Mascheroni plus the 5th harmonic number. This guy will be minus Euler-Mascheroni plus the 2nd harmonic number minus 2 times natural log of 2. You evaluate that, because the 5th harmonic number is just simple, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. You can add that. This is way easier to work with than just digamma raw. So you finally get to the answer of 2 times 137 by 60 minus Euler-Mascheroni minus 3 over 2 minus Euler-Mascheroni minus 2 times natural log of 2. That, my friends, is the value of digamma of 7 halves. And you can basically keep on generating these formulas as long as you're willing to calculate these partial sums for the harmonic number. You can have a computer do it for you if you're lazy, but this is a nice way of getting about things now with this formula. So I hope you enjoyed this video, guys, and I believe all our discoveries with respect to the digamma function and harmonic numbers are pretty much, that's it when you come to talk about them. Nothing more can be said. So please like, share and subscribe to my channel, guys. Recommend me to your friends. Spread the word of gamma digamma in the math community, and in the meantime, stay home, stay safe, keep doing math, and peace out. Signing off.